So these two guys, again, this Laplace was a French mathematician. Uh, Immanuel Kant was a German philosopher. Um, Anyhow, they started thinking about how the solar system formed, and back in the 18th century. So this is in the 1700s. Um, and there were people who noticed that as time went on, that there were these giant clouds between the stars, right? So you look out to the stars in our galaxy, um, and they didn't even know that there were other galaxies back then. Um, Anyhow, they would find these huge clouds, and they speculated, just pure speculation. They didn't have any actual evidence of this. That perhaps this is where stars would form. And they turned out to be right. That's why we still give them credit for coming up with this idea, even though they didn't have any actual. I mean, they could have been completely wrong, and we wouldn't be talking about them anymore. All right. So anyhow, now the thing is, these are different shapes, but eventually, when they begin to gravitationally collapse, and I'll talk about that in just a moment, they will get to be spherical, and then as the rotation increases, they will flatten out. It will go from being around a sphere into a nice, kind of like a pancake, a pretty thick pancake, but it's still a pancake. All right, and that's because of the conservation of angular momentum. Now, what gets these things spinning? And first of all, these have been around. These gas clouds. I mean, this is just one of them. There are literally thousands of them that we find in the Milky Way. Um, and we do nowadays. Of course, we can see these gas clouds in other galaxies as well. But by the way, not all galaxies. Right? It's only galaxies that have. If the galaxies have these clouds, there can be new star formation taking place. There are entire galaxies. They're called elliptical galaxies, where there's no new star formation taking place. Um, we believe all the gas is already formed into stars in those galaxies. All right, so ours is a spiral galaxy. It's still very rich in gas and dust. Probably still about anywhere from 15 to 20% of the mass of the galaxy. Although that number is still somewhat questionable. At any rate, there's 15 to 20% might still be available in the form of gas to become stars. All right, so if let's say you have one of these gas clouds, and it's many, many, many light years across. Okay, so and many times the mass of our sun, which is pretty much a medium-sized star. Okay, so one thing that people often get confused about is, why don't these things just collapse as soon as they form, right? If this thing is 4.5 billion years old, or even older than that, the galaxy's probably been around for about 13 billion years. The universe itself has been around for 13.8 billion years. So, if this has been around for let's say, 13 to 10 to 13 billion years, why hasn't it collapsed? All right. And so there are internal forces. It's usually heat. The particles that make this up are very far apart, but they don't like to be squeezed together, right? So in fact, they will resist being squeezed together, right? It's just a natural property of gases, and up to a point, of course. Of course, they can be squeezed together. Otherwise, we'd have no stars. All right. So what is it that causes these things to start to, one of these gas clouds that exist between the stars, to begin to collapse? And so what we believe happens is that there's some very early generation of stars, usually a very massive star, which undergoes its entire life cycle in a really short time. Like our sun, we expect to be around for 10 billion years. It's been around for 5 billion, so it's got another 5 billion to go. Um, but let's say this is a really massive star. I'm just making this up. Let's say this is a really massive star. It goes supernova, which means it explodes, right? And the shock wave from that explosion. So that's the death of a massive star. That shock wave goes, permeates out away from the star, and let's say it passes by a relatively close by, there just happens to be a close by nebula, solar nebula, and so what happens is that shock wave will cause the gas and dust to begin to collapse, and as soon as that happens, it will be spherical, and then the rotation starts, and it'll flatten out. And by the way, we do this we do simulations of this in our supercomputers nowadays, to see what would happen. You program the equations of physics into the some huge gas cloud, and you see what happens if there's a giant explosion nearby. And that's exactly what we get. You get stars forming, new stars from this. And not only that, nowadays, of course, we can actually peer into these gas clouds using the infrared telescopes that look in light that is a little bit longer than the visible light. And that light can pass right through the gas and dust. All right. These typical clouds are about 71% hydrogen, 27% helium. That should sound very familiar, because that's exactly the content of our sun, right? That's exactly, and then the rest of it is the rest of the elements on the periodic table, all the way up to uranium. All right, so let's see. You get these tiny little dust grains and mixtures of there's all sorts of elements in there. Silicon and oxygen, which are called silicates, iron, carbon compounds, and of course water ice, right? Because there's lots of hydrogen and there's lots of oxygen, right? Stars typically will produce carbon, nitrogen, and oxygen in abundance, toward as they go through their life cycle. So they're not just there's not just hydrogen and helium, which come from the Big Bang. There's also carbon, nitrogen, and oxygen that's available. All right, so this is so some kind of explosion occurred. Usually, we think it's a supernova, and the gas cloud begins to rotate. So notice here's a typical one about 3 light years across. I mean, that's huge compared to the size of our solar system and the size of other solar systems, which tend to be, maybe 100 astronomical units, which much smaller than this. Okay, so all right, so something gets it rotating, it begins to collapse and flatten out. There's an example of that. So let's say the disk starts out to be about 200 astronomical units across. And this is what they call a protoplanetary disk. And in some of these, we can actually see the protoplanets forming, and that they will clear out a path around their star. Let's see what else. So this is an actual photograph of one such example. This is another one, and so. All right, so let me talk a little bit about condensation. It's basically when a gas cools down when it has to, like, the temperature has to come down, the pressure usually has to come down as well, and the atoms or molecules that make up that gas will condense either into a liquid or into solids. right? So that's the idea of condensation, and so that takes place as these disks slow down. They rotate, they begin to collapse, and the gas molecules will in some cases condense, right, in these areas here where they're gobbling up lots and lots of material to form planets. All right, so now the condensation temperature is different for different things. Iron, for example, will condense around 1300 Kelvin. Just to give you an example, room temperature is about 300 Kelvin. Silicates will condense at about 1200 Kelvin. Water much colder, so around 300 Kelvin, which is room temperature. All right, a mixture of gases, materials with the highest vaporization temperature condense first, right? So, because as the temperature goes down, this stuff will condense first, and then comes the silicates. And that's why we get the rocky metallic worlds, at least in our solar system, really close to the sun. Condensation ceases when the temperature never drops, when it doesn't drop low enough. Let's see, the sun in the inner nebula out to about Jupiter, where it's too hot for irons and silicates to condense. Right. The outer nebula was cold enough for ice to condense. All right, so planets combine to form. These planetesimals start off as like little tiny things that where there's like little collisions, and sometimes these collisions will make the object grow in size, and when planetesimals grow, they will eventually form the planets. And we believe our solar system, in fact, had many planets, at least in the inner part of the solar system. There were many more than the four that survived. That's have currently survived. All right. So anyhow, there were lots of impacts. In fact, one of the impacts we already talked about, the impact that formed our moon, right? So that was a planet-sized object that hit the early Earth to form the moon. All right. Accretion is this process where things will come together through electrostatic forces. Like an example of accretion is like when you get dryer lint in your accumulating in your dryer, right? You put your clothes in the dryer and the lint will clump together. That's an example of accretion, right? But on a scale much larger than in your dryer. So these little bits of debris, which tend to be more rocky in the inner part of the solar system and more icy in the outer part of the solar system. All right. Eventually, the planets will clear out a path at whatever orbit they're in. And by the way, that's actually the last definition of what makes a planet that caused Pluto to be taken away from planethood, right? Because it didn't clear out the area in the Kuiper belt that it orbits the sun. All right, so you have the formation of planets eventually, lots of collisions, and yeah. All right, so here's some lots. I mean, we see examples of collisions all over the solar system, from the most distant worlds that we've encountered all the way in towards Mercury. There's been lots and lots of collisions over the course of the last 5 billion years that formed our solar system. So this is just an example of the different moons out there. The larger planets tend to have a lot more moons. The rocky worlds tend to have just a few, if any at all. Let's see. So the moons tend to be like little solar systems in and of themselves.